Hi, my name is Zachariah Carmichael. For this paper, I'm affiliated with the University of Notre Dame and Lawrence Livermore National Lab. My two co-authors are Tim Moon and Sam A. Jacobs. The title of the talk is Learning Debuggable Models for Multi-Objective Neural Architecture Search. So let's get into it. Machine learning automates the learning process, although it involves some human-guided feature extraction. Deep learning nicely automates the feature extraction on top of the learning, and it does so simultaneously. We've seen thereafter this neural architecture search come up, which actually automates the architectural design of deep neural networks, and it can usually be decomposed into a search space of possible architectures, a search strategy within that space, and some sort of performance estimation strategy, and that goes in between back and forth with the search strategy to find the best architecture according to your actual metrics. So what's next? Well, automation is proved to enable human progression, and within AI and deep learning especially, what's prolific is its trustworthy issues. So how can we actually bridge the gap between neural architecture search and explainable AI? And that's what we explore in this work. So there are three core approaches to XAI. There's post-hoc explanation, there's model inspection and debugging, and then there's intrinsically interpretable and self-explaining modeling. So there's a lot of evidence in the literature that one has a lot of fidelity issues. There's some literature that tries to prevent that, but there's still a lot of shortcomings. With intrinsically interpretable modeling, it's out of scope, it's interesting, and there's of course the interpretability accuracy trade-offs that is also debated throughout the literature, but in this work we're actually exploring the happy medium, this model inspection debugging, and we want to be able to produce neural networks that you can actually have a better idea of certain notions of interpretability, which we'll get into. So in formulating the problem, we have to actually formulate the search strategy and the performance estimation strategy, because we need to make architectures that perform well on a task, yet we can actually debug them under certain criteria. So we modify the performance estimation strategy. So in this work, we try to understand how latent representations can be used to understand both the model and the data. So we have a measure in the paper we call introspectability. It's just the surrogate metric for how debuggable the latent representations for a given architecture are. And formally, it is basically the expected value of the pairwise distances between the activations throughout a network between different classes. And it's nice with this definition because we can also incorporate the actual domain knowledge, such as from ImageNet, you have the WordNet label similarities, and you can learn semantic relationships and build hierarchies into your neural architecture search. So with the search strategy, we decide to go for a multi-objective approach, so we can actually learn the complete Pareto front between both accuracy and our surrogate metric for interpretability. We do so by employing the non-dominated sorting genetic algorithm and that basically just uses evolutionary algorithms to optimize a full front of solutions as opposed to just one that's aggregated through some sort of sum or mean of your different objectives. So with this proof of concept framework, we evaluate whether or not having these two objectives actually provides a greater what's called hypervolume, but basically what that means is we want to see if across different tasks we can learn better models that are debuggable according to our metrics. And as you can see across MNIST, CFAR, and ImageNet, we have a higher hypervolume when we do the multi-objective search. What this allows us to do is to have better calibration of models. So you can see here that for more introspectability, higher introspectability, our models have better calibration quality. What that also enables us to do is to identify mispredictions better according to this better calibrated latent space, as well as corrupted label detection. And we were able to accomplish this through this proposed neural architecture search. So this is a new research direction. It's still new. In the proof of concept, we show that surrogate metrics can be used to give more debuggable architectures, and future work should explore alternative and task-specific measures of interpretability. Thank you.